So today's class is Computer Organization Module 4 Lecture 2. So last day we learned about the control unit. So what is the control unit? The control unit actually causes the instruction to be executed by issuing a specific set of control signal at each beat of the system clock. That we know from the last class. And we know that each control signal actually do the specific type of micro operation. And in the objective of the control unit design means that we have to design the sequence of the control signal such that the data paths are open and different types of instruction are executed. That is the main objective of designing the control unit. Now we know that there are two types of design in the control unit. One is the hardware design control unit and another is the microprogram design control unit. Now you know that in the hardware design control unit there are mainly three components. One is the control matrix, another is the decoder, and another is the ring counter. So decoder actually decode the what type of instruction we want to generate, and ring counter generate the different timing signal, and control matrix actually combines these different two signals generated from the decoder and the system clock, that means the clock, and it will combine this and generate the sequence of the instruction. That is the function of the control matrix in the hardware control and the hardware generated control unit. Now today we will learn about the microprogram control unit. Now what is the microprogram? In microprogram control unit, actually the set of control signals that causes the specific micro instruction are termed as the micro that could be stored into the memory. That means the sequence of the micro instructions that is generated in a control unit can be stored in a binary form in a memory. Clear? Now here, suppose it stores as a string of the binary, and each binary point actually represents one control signal. When the binary point is set, that means that is 1, that means that control line is activated, and when it is 0, that means that is not activated. It will be clear if I give you one example. So using this binary string and storing the binary string in a ROM, that means the read-only memory which cannot be changed. Okay, we can easily make one control unit. Okay, how it is, it will be clear if I show the next example. Now the sequence of micro instruction is stored in a special type of ROM that is called the control memory. When processor wants to execute the control unit, different signal in the control unit, it will just fetch the different micro instructions from the control memory and it will execute according to the micro instruction. Clear? Now see how. So execution of a machine language instruction could be caused by fetching the proper sequence of micro instruction from the control memory and sending them out to the data path section of a computer. That means here different types of the control signal are stored as a binary form, and when the particular bit is 1, that means that particular control signal is activated, and according to this activation the data path is opened and data is transferred from one register to another register, because you already know that the instruction of execution of an instruction means actually the transfer of the data from one register to another register. Now a sequence of micro instruction that implements an instruction, you know that an instruction is a set of the micro instruction. So sequence of the micro instruction, because now you require the sequence the micro instruction that implements an instruction on an external computer is known as the micro routine. Okay, now what is micro routine? That will be clear again from the some example I have given later. Okay, now for this microprogram control memory, microprogram control unit, we will use the same digital computer we have used for designing the hardware control unit. Okay, so here you know that here these are the different types of special purpose register: PC, MAR, MDR, accumulator. B is a general purpose register. IR, instruction register, is a special purpose register. These all are the control signals there. There are total 16 control signals, and obviously there are clock there. Clear? So here this is the design of a total digital computer, small digital computer. Now we will design the control unit, the control unit using the microprogram technique. Okay. So before going to the whole details, this is the specification. You know, the specification of the computer is 12 bits wide bus connection between the register. RAM size is 256 into 12. You know why it is 256. Last day I told you. Okay. So then comes the signal L. L means loading the particular register or particular component. E means enable. That means the data will be transferred from the particular component to the bus, and loading means data will be transferred from the bus to particular component. This is the meaning of loading and enable signal. And instruction size, you know, that is the 12 bits. This is a 12 bits machine. Instruction size is 12 bits, where opcode is 4 bits, and remaining is the operand. That means the address bit is 8 bits. This is the specification of a small digital computer which I have shown in the previous slide. Now we know that this is the set of the instruction. You already know that this set of the instruction actually supplied by the manufacturer. Okay, means whenever you are designing a processor, you have to supply with the processor the set of the instruction which should be written in the ROM. Okay, depending on the set of the instruction, you have to write the program. Okay, if you write assembly level code, and if you write a high level code, then you have to use some compiler, or if you install some compiler, we will transfer your high level code to this assembly level code. This all of the code is the assembly level code. Okay, that means it has to transfer from the high level to the assembly level code of a particular machine. This is the set of the instruction used for this particular digital computer. So this all of the assembly level code. Clear? Now here there's one example how to use the micro instruction. Clear? Now see, you know that for any instruction, the main thing is the fetch the instruction. Clear? So fetch, you know already. What are the different micro instruction? We know that first is the PC to MAR. See, one correction here. I have already told last day that it should be PC to MAR, not MAR to PC. Okay. Program counter, which stores the address of the instruction to be fetched, will be transferred to the memory address register. Then from the particular memory in the memory address register, that means the particular instruction will be stored into the MDR, and from MDR to IR, and at the same time instruction register data from MDR will be transferred to the IR, that means the instruction register here it will be decoded, and in the same time program counter will be increased. So these are the 3 micro steps, and this total for fetching this 1, 2, 3, these are called the micro routine. Clear? These are the micro instruction, and here for fetching we require 3 micro instruction, and total this block is called a micro routine. And see here, for first micro instruction we have to activate EP and LM. For second micro instruction we have to activate the control signal R, and for third micro instruction we have to activate the control signal ED, LI and IP. Clear? So this fetch instruction, obviously we have to store one particular ROM. Why ROM? Because it is supplied by the manufacturer, and depending on this micro instruction, my control signals are generated in the computer. You cannot change this. For this reason, it has to be stored into the ROM, that means the read-only memory. You can only read this, that means user can only use the signal, it cannot change the signal. Clear? So here it is stored here. In the left hand side, first column is the micro instruction address. Clear? Why it is required? I tell later. First you see the control signal. First, these are the LB, EU, SA, EA, LA, EI, LI, ED, LD, W, R, LM, EP, LP, IP. These all are the 16 control signal I origin. Clear? See, this is the condition bit. This is the map. What is map? I will tell later. Okay, and this is the halt signal. You know, halt signal means it will stop the clock and all your execution will be stopped. And this is the address of the next micro instruction. Now first, for the fetch. So for the fetch, at the first address, this is the starting of the micro instruction address 00. Which instruction will be stored? It has to be made EP and LM1. Clear? EP and LM1. That means here, see here, EP1, LM1 at first. So all other bits will be 0. So this is a 16-bit EP1 LM1. It will be 6. All other are the 0. So this is the first micro instruction. Okay. Then after this execution of this micro instruction, that means if it gets this data, these two lines will be activated. All the lines will be 0. So data will be transferred from PC to MAR. After that, what is the next micro instruction? It has to go. Computer has to go. Next micro instruction is 0, 1. That means it will go to the 0, 1 here. Clear? Now in the 0, 1, which micro instruction is stored? Here the stored is 0, 0, 0, 0, 1, 0, 0. See here, in the second micro instruction, R is 1, because here we require the R control bit to be activated. So here R is only 1 and all other bits are 0. Clear? That means this will execute it. MAR from MAR to MDR. Clear? Complete. Second micro instruction complete. Then it will again check the address of the next micro instruction. So next micro instruction is 02. 02 means it will jump to the next micro instruction 02. What are the control signal it will activate? See here, ED, LI, IP. That means this should be 1, all others should be 0. See here. Here ED 1, okay, IP 1, okay, ED, IP and LI. This LI, it is also 1. Okay, that means all 3 bits should be activated, 3 control signal should be activated. They are 1 and all other bits are the 0. That means this is the last step, because IP means program counter will increase and EDLI means data will be transferred from the MDR to IR. So it's complete. Now it is written XX. XX means what is the function here? MDR data will be transferred from the data from the MDR will be transferred to the IR. What is the function of the IR? In the IR, it will decode the instruction. What is the decoding part? Opcode. This is a 4-bit opcode. I have already told 4 and 8. Total is 12. So 4-bit opcode, it will be decoded. After decoded, it has to go to the next instruction. Now, depending on this decoding instruction, it will generate what should be the next address. Clear? So it is nothing is written here. It can be any address. Clear? It will be clear from the next table which is stored into the ROM. Clear? So here I have shown you, this is a micro instruction address, this is the control signal, these are the 3 most signal, one is the map. Here see here one thing, here all other thing, condition bit and map are 0, and but here map is 1. That means when map is 1, the meaning is processor has to jump the particular address of the micro instruction. Here the address will be given after the decoding. Clear? That means here when it finds that this is a map 1, it has to jump to the address which is written here. Now see here, this is our basic control unit and this is the total ROM where the control instruction are stored. You know that ROM is a memory where there is the address. So this is the address is stored. Clear? And this is the opcode. You know this is the 4-bit opcode. So 4-bit means you know that 2 to the power 4. That means 16 bits can be, that instruction can be generated. 16 address instructions can be generated. Now left hand side column. This is the address of the micro instruction. And here see after each micro instruction, suppose fetch LDA, some space is given. That means this total thing is a 1 micro routine. Okay, this is another micro routine. This is another micro routine. So each instruction actually contains a micro routine. Micro routine means here the set of the instruction is written for the execution of that particular instruction. So fetch, I have already written. Then first, what is the specification of the RAM where this set of the instruction is stored? See here, micro instruction address. What is the total number of the micro instruction address? Obviously, total number of bits here is 5 bits because this is a hex code and this is a 4 bits, 0, 1, 2 up to F, 4 bits, and 1 bit is required for 0. So that is a 5 bit. So total number of address bit here is 5 bits required. That means what is the total number of address it can generate. Total number of address it can generate is 2 to the power 5, that means 32. Clear? 32 address it can generate. Okay. Now, one thing here is that always remember that here these are the control units, clear, and here these are the 3 extra bits we have to store. Extra bits means one is the condition bits, that means depending on bits it will jump to the another instruction. This is the map bit. Map bit, depending on this bit it will also go to the another instruction, and this is the halt bit, it will stop the total process. And this is the next address of the micro instruction. You know, here as the number of the bits is 5, here also number of the bits should be 5. So what is the total word size in the ROM? Word size should be this 16 bit, okay, plus 5 bit. Why 5 bit? Because this is the 5 bit, and 1 plus 1 plus 1. That means 1 bit, here 1 bit and 1 bit. That means 8 bit. So 16 plus 8, that means 24 bits. This is the width of the RAM. Okay. So this is the height of the RAM and this is the width of the RAM. So what is the ROM size? ROM size is 32 into 24. This is the total size of the ROM. Now, see here you can see this is the fetch. I have already discussed fetch. After after 02, after the third, when address is 02, after this instruction it will decode the instruction. So map bit means whatever address is written here, it will jump to the address. Suppose the instruction is STA. So for STA, first it will fetch the instruction. After in this line, it will decode the instruction. It is STA. So as it is STA, what should be the value of access? It has to jump from this map bits. Processor will know it has to jump to this address. What should be the address? As it is the STA, the address should be 5. The address should be 2. So this is 2 here. So it will jump from this fetch to directly to the STA. Suppose you want to execute the add instruction. So it will first fetch, it will go, it is common for all the instruction. This line, this line, this line. This is common for all the instruction. After that, it will jump to, as it is add, it will jump to the address 3. So it will jump, the processor will jump to the address 3 and then it will do the next micro instruction. Suppose processor has to store the particular data, that means STA. So first it will fetch, then it will go to the, what is the address of the store, that is the 2. So it will directly go to the 2 and then again it will execute 06, 07 and 08. Clear? In this way it will generate the sequence of the micro instruction, because it will generate, depending on the instruction, it will go to the particular address and generate the particular micro instruction in this case. Because see, in each address one micro instruction, 1 or 2 or more than 1 and 2 is activated. That means at that time, at that instance, that micro instruction will be activated and all other will be 0. Now see here, in this case, when the map is 1, see here, when CD is 0 and map is 0, both are 0, processor will jump to the address written here. That means processor, whatever address written here, it will jump. That means 01, it will jump to the 01. 02, it will jump to the 02. If CO bit and map bit both are 0. Now if map bit is 1, it has to jump to the address which it will get after the decoding of the instruction. Okay, that means after decoding of the instruction, if the instruction is LDA, it will go to the address 1. If it is store, it will go to the address 2. If it is add, it will go to the address 3. If it is sub, it will go to the address 4. In this way, this address, it is not written here, it will generate after decoding and processor control has to jump to that particular address. So when map bit is 1, processor has to jump to the particular address which is it will get after the decoding of the instruction. So again see the each instruction that is same. That means 00, both are 0. So it will go to the next. Whatever address written here, that is 04. Then 05, it will go to the 05. Then see here, after 05, it is written as 00. Why? because after the completion of the each instruction, see here 00 is written here, because after the completion of the instruction, it will again go for the fetch of the instruction, fetch of the new instruction. From where it will get the instruction? From the program counter. Clear? See here, after each instruction 00 is written, 00 here, 00, 00. After completion of the each instruction, processor has to go for fetching here. Here it will go to the fetch, here it will go to the fetch. That means after completion of the each micro routine, it will again start from the fetching the instruction. Clear? So here what is all is same, all are 00. The only difference is here. Here when condition G is 1, it will jump or it will increment. Okay. So if condition, this is called the jump on negative. That means if in the output result of the accumulator is negative, it will jump. Okay. Otherwise, it will increment. These two conditions has to satisfy. Again, I am telling that if the jump on negative, that means processor will jump if the result in the accumulator is negative. That means the carry bit is 1. Obviously, negative means 1. It used to jump. Otherwise, it used to increment. See here, if condition bit is 1, if negative flag is 1, it will jump to the OF. That means OF is written here. It will go to the not OF, sorry, 0F. It will go to the 0F. That means LP is equal to 1, EI is equal to 1. This control signal should be activated. Okay. Then it will go to the, here from it will go to a fetch. But if NF is 0, if CD is 1 and NF is 0, what it is called? It will increment. Increment means here the address is 0D, sorry, 0D, it will increment. That means the address will be 0F. So it will increment. So here three conditions we can see from the total ROM. One is that if map bit is 1, it has to go to the address written here. If MAP and CD bit is both are 0, it has to go to the address written in the micro instruction address here. And if CD is 1, okay, and NF is 1, it will jump to the address written here. That means 0F. And if CD is 1 and NF is 0, it will directly increment. Increment means it is 0D, it will go to the 0E. From here, it will again go for the fetch. Clear? So these are the total control, basic control unit we have written here. Now we will go for the design, how to implement this control instruction in a microprogram control unit. So here I have again written the particular add instruction. So this is the basic computer's address ROM. What is the function of the address ROM? Address ROM, okay. Previous one is the control ROM. This is the address ROM. Address ROM actually stores the address of the next instruction. That means the 5-bit address. Clear? So previous one is the control ROM, which stores the all the micro instructions. And here the address ROM, it will store the address of the starting address of the subroutine. So starting address of the subroutine fetch is 00. Starting address of the LDA is 03. Starting address of STA is 06. If I go previously, see here. This is the starting address. This one, this one, this one, this one, this one, this one, this one. These all are the starting address. So this starting address is actually stored into the address ROM of the total system. Now, what is address ROM? What is control ROM? How they are connected? How different addresses are selected depending on the MAP signal, CD signal, and NF signal? It will be clear from the next figure. So this is our architecture of the microprogram control unit. Clear? Now in the microprogram control unit, see here. First is the 34 into 24 bit RAM. I have already told you what is 34 because this is the control RAM where all the control signals are stored. See here from the previous figure. So this is the 32 into 24 ROM. This is the original ROM where all the micro instructions are stored along with their next address and CD, map, and voltage. So this is our ROM here. Clear? From the ROM, it will go to the micro instruction register, which stored in the micro instruction register. Micro instruction register is a special purpose register which stores the map bit, CD bit, all the control signal, halt, and CRJA, that means control ROM jump address. That means here, see here, this content, this total content starting from here to here, that is stored in the particular register. Clear? So this is the control bits, this is the CD bits, map bit, alt bit, and this is the CRJA, control ROM jump address. Clear? This is the control ROM jump address. Clear? Now see here, this is the control ROM jump address, that is the 5-bit. You know, instruction signal is the 16-bit, map 1-bit, CD control bit is 1-bit, alt is 1-bit. So 16 plus 5 plus 1 plus 1 plus 1, total 24. So this control bit will generate these 24 bits, because 32 is the address, 24 is the number width, that is the width of the data, you know, from the specification. Clear? So this control bit. So after throwing this control bit will generate this, 3 conditions arise. I have already told you. One is it may go to the next address, that means what is written in the XX in the fetch instruction. So that means here the opcode feeds on the instruction on register. That means depending on the decoder, it will generate the opcode. Where 16 is to 5, because 16 is the opcode, 2 to the power 4 is equal to 16, and why 5? Because that is the 5-bit is the starting address of the subroutine. I have already told you. So this is the address ROM. So this is the address ROM. Clear? Here there will be 16 bits, because 2 to the power 4 means 16, and 5 is because of this, because this is the starting address of the subroutine. So this is the 16 into 5 address ROM. Clear? This is the control ROM, this is the address ROM. 2 ROMs are used. So this is the address ROM. So this is the starting address. 5 bits means the starting address. Okay. So it will go from here. This is the next address. Okay. Now this is the starting address, and another thing, that is the increment. Where increment is required, I have already told, as the jump negative. If it is jump negative, it may increment, it may go to the address written in the CRJA, or in the fetch, the last line XX, whatever this is written here, that means processor may jump to that address also, depending on whether the last line of the instruction is, that means the where the decoding is taken place or not. Clear? So these are the 3 types of address processor has to go after the fetching of the instruction, or after the completion, after in the micro instruction, or after the completion of the each micro instruction. So these 3 conditions, that means 3 inputs, the inputs are given as 0, 1, 1, 0, 0, 0. Processor has to choose out of the 3 inputs 1. Okay, that means whether it will take the data from here, here, or here, processor has to choose. That means this is the one data selector is required for that. Okay, why data selector? Because processor has to select either from this, it will take this 5-bit data, or it will take the data from CRJA, control ROM jump address, or it will increment the particular address which is stored into the control ROM jump address. That means 3 inputs line here. Processor has to select out of 3 only 1. That means it has to use one selector. What is data selector? You know that multiplexer is called a data selector. So here one multiplexer is used. Yeah. Now the question is, if the multiplexer is used, you know from the lab, multiplexer means here requires some select lines. Depending on the select line, it will find out what will be the output of a particular input. That means if particular select line is activated, so this will be activated, or this will be selected, or this will be selected. So when the select line is 0, 1, here the 0, 1, 1, 0, 1, 0, this is written is when the bit is 0, 1, these are the select line, 2 lines here. When the 0, 1, these 5 bits will be selected. When this is 1, 0, this data will be selected, because this is 1, 0, 0. When the 0, 0, this data will be selected. That means that this will be incremented. Again, I am telling, when this is 0, 1, processor has to select the data from the address ROM. That means the starting address of the subroutine. Clear? When it is 1, 0, processor has to select the data, select the address which is written in the CRJA, that means the control ROM jump address of the micro instruction. So CRJA 5-bit instruction will come here. Clear? If it is 0, 0, processor has to only increase the data. This condition actually happens in case of the jump on negative. So this here in the table, Here there are the 4 conditions. Okay, because there are 2 lines, we can generate 4 conditions. 2 to the power 2 is equal to 4. So when map is equal to 1, you know select is 0 1. 0 1 means when map is 1, I have already told it has to go to the, that means the x is written here, that means it has to go to the address which is generated from the opcode instruction. That means the decoding of the opcode. That means from the, it will take the data from address from. So 0 1. Good. When map is equal to 0, CD is equal to 0, what will happen? It will 1 0. 1 0 means this data will be incremented. See here, when map is equal to 0, CD is equal to 0. See here, map is equal to 0, CD is equal to 0. It has to go to the address written here. Clear? So it has to go to the address written here. That means CRJ address. Okay. Now when map is equal to 0, CD is equal to 1, and NF is equal to 1, I have already told that will be 1 0. 1 0 means whatever address written here, it has to take. Otherwise, when NF is equal to 0, okay, that means negative flag is equal to 0, it has to what? It has to increment the data. So that is, it will be 0 0. Clear? See again, if I go here. See here, if NM is equal to 1, it has to go to the OF, whatever written is here, and if not, it will increment. Okay, it has to increment. So 0 0 means the increment. Clear? So depending on this, it will generate the sequence, you know, because if particular address is generated, it will fetch. From the fetch, it will generate the 5-bit address. It will go to that 5-bit address. Again, it will instruction in the if each micro instruction, it will take the data from CJRA. Exception is if there is only CD is 1, that means the jump on negative, then either it will increase if the number is negative. Okay, if the number is negative, NF is equal to 1 means if the number is negative, it will go to the address written in the CRJA. Otherwise, it will jump to the, it will increment, increment the particular address from the micro counter. Okay, micro counter means it will each clock pass, it will generate the one counter. That means first it will take the data first from one address, then it will next address, then go to the next address. This counter is, this operation will be done with the help of a clock and with the help of a micro counter. Micro counter means same in the same way, just like the ring counter, it will count the 1 2 3 4 in this way, the sequence it will count. Okay, so this is the thing, it will be designed. Okay, in this way, this is the microprogram control unit. So here, see here, what is the difference between here? There is no decoder is used actually, and no control matrix is used. Control matrix is the most important in the hardware control unit. Here there is no concept of control matrix. Here only the main component here is the control ROM, which stores the all the micro instructions. Obviously, this is ROM, and this is the address ROM, which stores the starting address of the routine of the particular instruction, micro routine of the particular instruction. So these are the main, and with the help of this multiplexer, it will choose the what should be the next address, whether it should be go to the address taken from the address ROM, or it has to take the data from the CRJA, or it has to increment the particular address. Clear? So this is the microprogram control unit, and in using this microprogram control unit, the sequence of the instructions are generated in a system. Clear? So you know these are the sequence of the instruction that I already told in the matrix of the control units. This is actually required for the hardware control unit. You can compare this with the previous figure, how to generate this matrix here. That means the same thing will be generated in the ROM. Clear? So if I compare with the hardware control unit, Hyper microprogram control unit, remember most of the computer today use are microprogram control unit, because if you use hardware control unit, the problem is it is not flexible. Flexible means you cannot change the number of the instruction, you cannot expand the number of the instruction, okay, or you cannot increase the number of the instruction, because that is dedicated circuit. You know that hardware is a dedicated circuit, so it is not possible for that. So it is not flexible. To make the system flexible, today manufacturers actually mostly use the microprogram control unit. Clear? But always remember, hardware is a dedicated circuit, hardware control unit, obviously speed is the highest. Because here no fetching instruction is done, no access of the memory is done in the hardware control unit. So if you design something where there is no requirement of flexibility, no change of instruction, you must use the hardware control unit because speed is the highest. Your only time required is for the gate delay. But in case of the microprogram control unit, here requires the fetching of the instruction, fetching of the particular memory, which requires the memory access time. You know, memory has some memory access time. So no such time is required for the hardware control unit. So this is the difference between the hardware control unit and microcontroller control unit. So that's all for today, and thank you for watching the video.